Hello everyone, thank you for joining this session. I'm Stéphane Truesch from EcoBird, a French SME specialized in wastewater treatment with constructed wetlands. I'm pleased today to present you this presentation about construction and operation of treatment wetland treating raw sewage. Well, at first I would like to point out the use of a vertical flow constructed wetlands for the different applications like on-site sanitation, raw domestic sewage, which is the focus of this presentation, industrial wastewater, sludge and septage treatment, and also stormwater runoff and combined sewer overflow. So this is the different application for this type of vertical flow constructed wetlands. As a first step, whatever the process, the preliminary design consists in evaluating the site for the wastewater treatment plant implementation with a special focus on the local constraints, like the shape of the area, the geotechnical and topographical characterization. These surveys will make it possible to evaluate earthworks, requirements and resources to establish the 3D layout and drawings of the structures and basins, and also the altimeter setting in order to maximize gravity flow between the inlet and the outlet. Thanks to the topographical survey, the earthworks modeling is a necessary step in optimizing the balance between cuttings and backfill for the creation of the basins and their embankments, as you can see here on the picture. Now let's have a focus on the different components from the inlet to the outlet of the wastewater treatment plant. As a first step, we can see here the bar screening, which could be automatic or manual. Then here we've got a primary siphon, which allows an automatic and gravity batch filling, followed by a distribution manhole to direct the water to one of the cells of the treatment stage. And here you've got the vertical flow treatment wetland himself, which is connected to a collection manhole before discharging treated water in the recycling body. The both stages of the French configuration are sealed from the ground with a geomembrane and are filled with gravels with an increasing particle size from the top to the bottom. The water is fed through appropriate feeding pipes, and then the water percolates vertically through the attached growth biomass fixed on gravels, and is then collected at the bottom of the filter through a drainage networks, itself connected to the atmosphere by ventilation chimney in order to ensure a passive aeration. Earthworks for basins must be carried out in accordance with good engineering practice. A good complexion and shaping, of course, will drive the quality and durability of the works, whatever the nature of the topsoil. Next comes the waterproofing of the basins, which involves installing a geomembrane stacked between two layers of anti-puncture geotextile, as you can see here. And the geomembrane could be made of HPDE with walls welded on site, or with EPDM in one piece for small surface. The geomembrane is preferentially anchored in the embankments, as shown in this section. Next comes the installation of the drainage network made with slotted PVC pipes. You can see here in the picture. And the slot width is ranged between 7 and 10 mm in order to avoid any risk of clogging due to the roots penetration or biofilm accumulation. The minimum drainage density of the drainage networks is about 0.25 meter per square meter of filter surface. Each drain needs to be connected to the atmosphere through an aeration chimney, which is essential for the air diffusion within the filter and to ensure aerobic biodegradation. Then the different layers of gravel are laid within the filter, taking care not to damage the waterproofing of the basins. The filtering gravel should have a low calcareous content to not degrade over time due to erosion or any acidification of the treated water. The feeding network that distributes raw sewage on the first stage differs from a gravity mode here on the left to a pumping mode with a lift pump here in this picture. The minimum number of feeding points should reach 1 point per square meter on the first stage of treatment, while the distribution ramps on the second stage should provide a higher number of feeding points to ensure a better water distribution all over the filter surface. In all cases, the distribution pipes are designed and implemented to prevent all risks of water accumulation between batches, which can lead to freezing in winter or clogging due to deposits accumulation. Each cell of a bed must be hydraulically separated from the others by the implementation of a separation wall that could be in polycarbonate, like here on the picture, or in concrete and welded directly on the membrane. This allows a perfect resting period without any leaking from one cell to another one. The freeboard above the filter surface must be high enough to ensure a sludge accumulation of 20 cm as a maximum and should also ensure an additional storage capacity of water during rain events. So here, for example, the left, the sludge capacity and the freeboard is too small, is undersized, and here on this picture you can see that the concrete wall does not ensure a good waterproofing between two cells. Concerning the intensified wetland equipped with forced aeration, the principle is still the same than the French design because it receives directly raw sewage on the filter surface. But here the filter has a saturated and aerated zone of 1 meter deep, as you can see here on the picture on the left. A dense aeration network rests at the bottom of the filter and is connected to a blower which transfers the oxygen needed for the oxidation of the organic matter and the nitrogen coming from the raw sewage. Here you can see on the picture the implementation of this aeration network that can reach easily several kilometers long. Here also are a few pictures to illustrate the installation of this aeration network. And on the right, you can see the first aeration test with the bubbles here. Aeration tests to ensure that each line is properly connected to the air feeder you can see here. So these first tests are really important to ensure that the aeration networks is reliable. Blowers generally used for this type of systems are generally low pressure blowers operating at 200 millibars, the maximum, with airflows rarely exceeding 800 cubic meter per hour for a large wastewater treatment plant of 2,000 people equivalent, for example. So here on this picture you can see this kind of blowers, which is generally installed and implemented in the technical room. Now I propose to move on the maintenance and operation tasks of this type of treatment wetland. And it's important to point out that even if natural treatment wetland need low maintenance, it's not a system that can be left alone. Here on this picture you can see a treatment wetland without any maintenance since maybe several years, as trees are growing within the filter. Little chance here that the geomembrane is still effective. The main maintenance and operation tasks are relatively simple and are briefly presented here on this slide. They consist in the bar screen inspection and consist also in discharging screened waste every week. The control and the cleaning of the siphon or the pumping station, which consists in removing the grease accumulated on the siphon, the pumps, or the float level switch, for example. It has also to be ensured twice per week the filter rotation by opening the supply line to the cell to be fed by moving these pipes in the manhole here. The checking and the cleaning the feeding pipes has to be done once per year. Here on the picture you can see the sludge accumulation within the pipes, which has reached a critical level. During the first years of commissioning, while the reeds are still young and poorly developed, the operator has to control weed proliferation by hand pulling and taking out these weeds. And every year it is recommended to harvest the reeds before winter. This action limits the rate of organic deposits accumulation. And finally, once the sludge deposits reach around 20 centimeters after 10 to 15 years of operation, it has to be removed, and these specific tasks is more detailed further in the presentation. Concerning the first aerated wetland, the additional operation task rely on the blower and aeration networks maintenance. This consists of changing the air filter of the blowers every 2 years, and also to have a regular bleach online injection within the aeration networks in order to prevent biofilm accumulation that can grow within the aeration pipes. This consumption of bleach that can be stored within the technical room is really low and quite efficient. Finally, once the accumulated sludge on the filter surface reaches about 20 centimeters after 10 to 15 years of operation, it has to be removed. This withdrawal operation could be done with a mechanical shovel, like on the picture here, and this could be done from the dikes or by direct access into the beds, which is the case here also on the picture. So the sludge with a high organic quality can be easily recycled for agricultural use by land spreading, for example. This end-time operation does not have a negative influence on the restart of the reeds, as they will grow again from the roots which remain in the filter or below the surface. So here on the picture you can see the filter once after the sludge removal and the regrowth of the reeds 1 month after. So thank you for your attention, and I hope that this presentation has enlightened you on the construction of the vertical flow constructed wetland and their maintenance tasks. And of course, I remain available for any further questions you may have. Thank you.